Alright, ladies and gentlemen, the integral fun continues. If you remember correctly, we really try to focus on, we've done a lot with integrals. We have found many ways to evaluate integrals. We've put a lot of emphasis on it. But remember, when we find integrals, we're really trying to find areas under a particular curve. And we're going to continue that concept here with finding areas between curves and areas that are enclosed by intersecting curves as well. Now, if you remember correctly, we first kind of introduced find the area of the curve. We used our RAM approximation, our rectangle approximation method to really kind of focus on, let's say, for instance, you had an area under the curve that was something of the nature like this. And then all of a sudden, remember, you found a bunch of rectangles, that sat there and were pretty close to what we wanted to try to find. We wanted to find the good approximation. I know this is a terrible drawing, but you get the picture of really what we were trying to find of the area of all of those rectangles that were pretty much the area under the curve itself. And now, that's thinking about it in terms of the x-axis. And so we thought, okay, well, if I'm trying to find the area above the curve, it's that particular, approximation of those rectangles. But you could also take it underneath the curve as well, too. And it's really the area above minus the area below, and that's what's going to give you the entire area of the whole thing. But now let's say, for instance, we're diving into something that really is a little bit different. Let's say you've got a function that looks something like this. We'll call this y equals f of x. And then let's say you have another function that looks a little bit more so like this. We'll call this y equals g of x. Well, now, if I said find the area under the curve, the question that you might ask me is, hey, what curve are you talking about, right? Because I might actually be saying find area between the two curves that we're dealing with, right? And this gives us a nice little insight into areas of multiple functions in the same concept. Well, the same thing would hold true. You're really trying to find your approximation of all of these little rectangles that go with everything inside of these curves. And again, this is not obviously a good drawing here, but you get the picture. You're trying to find the exact same approach as we did for our RAM approximation of our area under the or above the x-axis or below the x-axis, right? And this is the exact same thing. However, we're now dealing with two different functions. When we deal with two different functions, we have two things to worry about. And we can use this formula to find the area between two curves. The area between two curves, we'll call it f of x and g of x once again, over an integral a to b is the integral, it is still there, ladies and gentlemen, the integral, alright, of a to b of the subtraction or the difference of f of x minus g of x as long as f of x is greater than g of x, aka the values of y are above g of x. Okay? So that's what we're going to be really looking on into for this example here. Now, let's take a look at what we can actually utilize this for. Let's say, for instance, I want to find the area of the region between y equals secant squared x and y equals sine of x from 0 to pi over 4. So we need to find the area above these curves. Now we can graph these and kind of get a little visual for them. Let's just do that real quick. I'll do a rough little sketch. We'll have the secant squared somewhere up here. We know our sine is going to go somewhere down here. So here's our secant squared. Here's our sine of x. We want to find the area in between here. but specifically, since it says from 0 to pi over 4, you know, roughly pi over 4 is here, so we are actually really concerned with all of this area that is right here. Well, that is where our integral is going to come into play. So the area will equal the integral from 0 to pi over 4 of f of x, which is secant squared because it is greater than sine of x, so of secant squared x minus sine of x dx. Now we integrate both of these. It's a basic integration. The antiderivative of secant squared will be tangent x. The antiderivative of negative cosine, or negative sine of x is going to be a negative cosine, so I'll be positive now in this case. And then we want to evaluate that from 0 to pi over 4. Now substituting pi over 4 and 0 into these, we're going to get that we are at square root 2 over 2 units squared. All right, ladies and gentlemen. So now let me make this very clear. Yes, this was a very basic example to start some things on off with, okay? Integration was super simple in this concept. Now, our integration rules and our methods aren't going anywhere. Please make sure we know that. There could be by parts, there could be substitution, there could be natural logs and trig functions and inverse trig functions, and all of those as well too. This is very basic to get things rocking and rolling here. Alright, let's get one a shot on your own and make sure that we're on the right path here. So what I want you to do is to find the area between y equals 1 and y equals cosine squared of x. And I'm looking, in this case, from 0 to pi. Alright? From 0 to pi. Alright, give this one a shot on your own. Now, I'm not going to, I guess, roughly, I guess I'll put pi half in there kind of for your answer in there. But now, let me make this very clear. On this one, this example is given from a graph in which I'm not showing the graph for. And so it's roughly about 0 to pi in here. So if you're not 100% on pi halves, like I said, don't freak out completely, but it should be pretty good as to where you are. So give this one a shot on your own and see where you come up with. Have a great one. We're on to the next one.